Welcome to your own channel of Right Funda. Here is another interesting problem from hinged rod type of things, and there is a collision happening with a hinged rod system which has been hinged at one point. Let's discuss the question. Read the question first. Two uniform and identical rods, each of mass m, have been joined as ideal pinpoint connection at one end as shown in the figure. System is kept on a smooth horizontal surface. If a mass m moving with a velocity v0 collides with the junction and comes to rest after collision, find the velocity of the hinge up just after the collision. Hinge point just after the collision. So what is given? This is two rods are there, and the rods have been hinged at this point. They have been hinged at this point. Not shown. They hinge at this point. So these two rods can rotate about this point and they can freely move this frictionless surface. Another particle of mass m, it came and collides with one. This each rod having are given the mass m and m masses are given. And as it strikes this one, then what is the velocity? They are identical rods are there. You can take their length as LL also you can take. They're not given, not required of course. So just after collision, what will be the velocity of the hinge point has been asked. So once you have understood the question, you could try pause the video if you wish to do and try yourself. After that, you can again resume and again see the solution. Now, hope you have solved this problem. Now, what is there is that this particle came and strikes with this mass came and strikes with this one. After that, what will happen? The rods will be going in plane general motion, both the particle. And question is saying that this particle came to rest. So after that, if you want to draw the free body diagram, suppose this happened, not free body diagram exactly. What happened after the collision? After the collision, if you see this particle came to rest, become 0. And this suppose this go with a velocity v1 and this goes with a velocity v2. This is the center of mass of this rod and this is the center of mass of the other rod. Two masses there. C1 I have taken, this is equal to C2 I have taken, this is the O point I have taken. They are the velocities there. Also they will have some angular velocity. Suppose I say that this is angular velocity equal to omega 1 and angular velocity of this rod is equal to omega 2. And we know omega does not depend on the point. Omega is omega of the point. And V1, V2 are we have taken the velocity of the center of mass of the rods in the ground reference frame. So this will be going with this. And after some time, suppose this is the first situation here, first instant. Then next instant it came and collided with this one. And what will happen the next instant? If you want to see the situation, this rod may look like this. Okay. So this particle will be there and this will be going. It will be moving with v1, v2 velocity. This will be v1 velocity and this is equal to omega 1, omega 2. But this velocity will be changing after some time. So now new velocity, some velocities will be there here. And it will be happening like this. So, but question is asking after collision, what will be happening after this? So we can apply we cannot apply conservation moment of the particle, not for the rod system, but for the whole system we can apply conservation of linear momentum for the system can be applied. And applying conservation linear momentum for the whole system, I can write m v0 is equal to, suppose mass of the particle was m, and this m v0 is equal to mv plus mv just after collision. So for this velocity v1 v2, because this identical are there, so why I will be taking v1 v2? I will take the same velocity I will be taking because this velocity is identical, so the velocity of this will be same. Similarly, this identical there, so omega also will be equal to same because rod will be going like this identical situation. After collision, their velocities are v and v. Omega this velocity of the center mass of the rods are v and they are moving with angular velocity omega. Okay, so from this I can calculate the velocities of the each body's center mass to be equal to v0 by 2. Okay. Once velocity by 2 velocity they will be going, then I can require omega also. So if I apply conservation of angular momentum of the system of any one rod, let's apply conservation of angular momentum of any one rod. Okay. About the hinge point. About the hinge point we apply the conservation angular momentum. Then what equation we can write? Initial angular momentum, because the particle was here, particle was going like this, so the angular momentum was 0, RCM cross PCM for particle, RCM cross PCM. About this point I am applying conservation angular momentum, so angular momentum was 0 over there, and this also we are achieving. So in before collision they were 0. After that each draw, suppose I am to the right rod I am doing, so it will be having plane general motion, so RCM cross PCM, RCM will be L by 2, into PCM, mass of the rod, into velocity of center of mass of the rod, into ICM into omega. I can apply that one and I can write this one. So this we have written for the left rod. Suppose we could have written for the right rod also. Left rod we will be writing for the left rod, this is equal to RCM is equal to minus I cap direction into BCM in the J cap direction, minus I cap minus K cap, and this one. If I written for the right rod, then only this will be plus and this will be equal to minus. This omega will be minus, this will be plus will be there. Because right rod will see then RCM cross PCM from this, and this will be equal to anti-clockwise direction, RCM plus PCM will be there, and this will be in the clockwise directions. Okay. So this we have written, and from this if we simplify this equation, from that we can get the value of omega to be equal to 6b by L K cap. Okay. So we got the two things we got: velocity of the center of mass of the rod we got. Suppose for example with this we got the center of mass of the left rod we got, and this is the angular velocity of the left rod also we obtain by applying respectively conservation linear momentum and conservation of angular momentum about the hinge point. We got these two equations. So this will be in the I cap direction, this is an I cap direction, and this will be equal to K cap for left rod and will be equal to minus K cap for the right rod. Okay. So once we got the VCM and what omega we got, then from this we can simplify this one, and this V is equal to V naught by 2. So we have got the V is equal to V naught by 2. So I'll get this result we can obtain in terms of V naught. I got in terms of V naught. Now I can find the velocity of hinge point. Question asking, suppose hinge point name is J point. I will get the hinge point name. Velocity of J, hinge point is of ground equal to velocity of J because of C1 plus velocity of C1 which is of ground. I can write V equal to omega cross R, and I can put this equal to omega is equal to 3 V naught by L K cap, and L by 2 minus K cap cross product of that, and plus V by 2 J cap. So I got this two equations, and if I add these two equations, 3 by 2 V naught plus V naught by 2 equal to 2 V naught J cap. So I got the velocity of the hinge point. We calculated the velocity of hinge point is equal to this one. So what we got? This is the velocity of the hinge point. Hinge point is a J point with respect to ground. But last problem also we discussed similar type of question, but the force related problem, acceleration calculated. Today we calculated this velocity of the hinge point equal to 2 V. But many people have the doubt, many people have the confusion like this. They do last problem also I discussed same thing. Then they apply the conservation of linear momentum for the whole system, and directly not taking the individual part, they take whole as a system, and they end up with the wrong result. What they write? M V naught is equal to 2m into velocity of center of mass, and from this they get the velocity of center of mass to be equal to V naught by 2. But we have obtained that this point is a center mass point. This point with velocity, what we have calculated today is not that velocity of hinge point equal to 2 V naught. Velocity of hinge point came out 2 V naught, but they got this. So is this equation wrong? Is this equation what they wrote is wrong? No, the equation wise is not wrong is there. Equation wise is not wrong, but interpretation wise is wrong. Why? Definitely, because whole system we can take a velocity of center mass can be calculated just after collision, the center mass velocity will be there. But as I told in the last problem, this is also same thing is there. This center of mass point and hinge point, they are not the same thing. Hinge point and center of mass are not the same point. Coincidentally, they coincide at that instant. Initially, both hinge point and center of mass point are here. But as time passes by, you will be seeing center of mass and hinge point will be separated. After some time, will the center of mass of this here, center of mass of this here, somewhere center of mass will be here, or somewhere it will be here. But the hinge point will be going here. So J point will go here, center mass will be going here. They are not thing. They are not moving the same place. Initially they were the same point. Initially they were somewhere here. Same point where J and C was here. But by center mass point has traveled from this to this, the hinge point travel from this. So that definitely they must be moving at different velocities, different accelerations. So what we got by this equation, the velocity of center of mass, that's was true. But velocity of center of mass is not equal to velocity of hinge point. So hinge point to be calculated, always take the master rule that if this type of not rigid system is given, which is doing plain general method, this is a rigid system, this is a rigid system. But the whole thing is not a rigid system. If this type of problem is there, take each individual part separately and apply whatever basic concept you know, conservation linear momentum, conservation angular momentum, whatever we do. But don't take whole as a system, you'll get the misleading result. Yes, you'll be getting velocity of center mass, there is no doubt in this case, but question is not active with the center mass velocity. Question is asking about the hinge point velocity, which is Hinge is a different thing, a center of mass is a different thing. They may be at that point same thing they are, but they are moving at a different velocity, they are moving at different acceleration. Hope you understood the problem, and we solve this type of problem, two problem, one for the force, another for the velocities of this. Once we get the velocity of center of mass at this point, angular velocity of this point, now we can calculate the velocity of this point also, velocity of this point also, any other point velocity can be calculated. Any other velocity can be calculated. So take as a homework, calculate the velocity of the one end of the rod and write in the comment section what you got the velocity of any one end of the rod velocity. And also calculate that what is the loss of kinetic energy in this problem due to collision, how much energy is lost. Calculate this and write in the comment box what answer you got. Hope you have understood the topic.